Tonight on Nova, trek to the top of the world on an expedition that's putting a bold new theory to the test. Hunt for clues in a chilling mystery.
Will you ever be able to find enough fossils and date them well enough?
Do the Himalayas hold the key to the origin of the Ice Age? Did these mountains rise up and forever change the world's weather? Science takes a stab at cracking the Ice Age. Nova is funded by Prudential.
Living well isn't about being rich. It's about freedom and independence and taking control of your future. So make a plan. Be your own rock.
And by Merck.
Merck, pharmaceutical research. Dedicated to preventing disease and improving health. Merck, committed to bringing out the best in medicine.
The Corporation for Public Broadcasting and viewers like you.
The Himalayas are one of nature's finest masterpieces. Rising 5 miles into the sky, they are the highest and steepest mountains in the world. The creation of this magnificent landscape is one of the most dramatic tales in the Earth's history. Now, scientists believe that these mountains could hold the answer to one of the Earth's oldest mysteries, the cause of the Ice Age. The Earth formed about 4.5 billion years ago in a violent inferno of rock and gas. Since then, the climate has almost always been hot. For hundreds of millions of years at a time, most of the land was lush, tropical forest. During these extensive warm periods, no ice seems to have existed anywhere on the planet, even at the poles. Punctuating this long record, though, are several mysterious cold spells, or ice ages, when vast portions of the Earth froze. The last ice age, probably the most severe of them all, started about 40 million years ago. Around that time, as if the Earth's thermostat got turned down, temperatures gradually started falling. Eventually, it got so cold that immense icebergs cluttered the oceans. So much water was frozen solid that sea levels dropped about 400 feet. Ice sheets up to several miles deep covered much of the Earth's surface. In the northern hemisphere, those ice sheets have been growing and retreating in fairly regular cycles for the last 2.5 million years. Eventually, ice crept as far south as modern-day Nebraska, Chicago, and New York. About 12,000 years ago, that ice sheet shrank away. Scientists think the changes in the Earth's orbit explain the repeated growth and retreat of these ice sheets. The greater mystery, though, is why it got so cold in the first place. What caused the long, slow cooling trend after it had been warm for so long?
The Earth's climate has been warm for hundreds of millions of years. Then that Earth began to change. It began to get cooler, first slowly. By about 40 million years ago, there was ice in Antarctica and in Greenland. It got colder still, and then almost in a twinkling of an eye, huge ice sheets began to form, eventually reaching depths of well over a mile. Why did that happen?
That question has baffled scientists for over a century. Answers to the Ice Age mystery have ranged from fluctuations in the sun's output to dust injected into the atmosphere by large volcanic eruptions. Even life itself, all the animals, plants, and other organisms on Earth, is believed to help regulate temperature. Now, adding to that list, some scientists are proposing a geological explanation for the Ice Age. It is a controversial new idea that links changes in global climate to one of the Earth's most impressive geological features, the Himalayas. Even from space, these mountains stand out like a giant scar on the face of the planet. This is some of the most rugged and wrinkled terrain on Earth. To investigate whether the formation of these mountains somehow caused the Ice Age, an international team of scientists recently ventured to this remote corner of the world. The expedition began in the Himalayan city of Lhasa, the ancient capital of Tibet. Now controlled by China, Tibet lies just above India in the heart of Asia. On its southern edge are the Himalayas. To their north is the vast Tibetan Plateau, about 1/3 the size of the United States. Averaging more than 15,000 feet above sea level, the Tibetan Plateau is the highest terrain on the planet, the roof of the world. It is so remote that half the population of the plateau still pursue the traditional nomadic lifestyle of their ancestors. Scientists have long sought access to this region, but few have ever been admitted. Protected by the Himalayas, traditional Tibetan society always discouraged exploration by outsiders. Until recently, that society was organized around a Buddhist religious hierarchy whose customs had remained unchanged for centuries. All that came to an end in 1949 when China invaded Tibet. A few years later, the Dalai Lama, Tibet's traditional leader, fled across the mountains to India, fearing for his safety. As China tightened its grip, much of ancient Tibetan society was obliterated. This region is still severely restricted under Chinese communist rule. The Tibetan Plateau remains virtually unexplored. Scientific expeditions to this part of the world are rare and only for the hardy. This one, in search of clues to the start of the Ice Age, would take more than 2 weeks to traverse about 1,000 miles of the rugged Tibetan Plateau. The air at this altitude of 15,000 feet is thin and even in the summer, temperatures drop well below freezing at night. The scientists on this expedition included those who support the idea that the Himalayas caused the Ice Age, as well as some who are more skeptical.
Take some pictures of you guys.
While the sights in this region are always magnificent, this team was here to do more than enjoy the scenery. For those who know how to read it, this landscape tells a story. It is the story of the birth of the Himalayas and of what happens when continents collide. The surface of the Earth is divided into huge moving plates. These plates separate at massive volcanic ridges the size of mountains on the seafloor. Magma from deep inside the Earth wells up between these ridges, spreading outward and forming new crust. This process is known as seafloor spreading. It is happening all the time and accounts for about 80% of the world's volcanic activity. The continents were originally in very different positions than they are today. The plates are constantly in motion, and India and Asia were headed toward each other on a collision course.
150 million years ago, I would have been standing on the southern edge of the Asian continent. And far away to the south, there would have been an ocean, the Tethys Ocean, stretching for thousands of kilometers, and on the other side of that ocean, there was the Indian continent. Now, plate tectonics dragged the Indian continent closer and closer towards the Asian continent.
About 45 million years ago, India crashed head-on into Asia, but it didn't stop there.
Since that time, it has moved 2,000 kilometers north, plowing up mountains in front. The most spectacular consequence of this collision between the Indian subcontinent and the Asian continent is the Himalaya.
Here we can see strata which originally would have been laid down horizontal. And now they've been deformed, they've been upturned, they've been folded, they've been totally scrunched about, showing the impact of that major collision.
As it crashed into Asia, the upper layers of the northern edge of India were sheared off and stacked up over the collision zone, forming the Himalayan mountains. India is still pushing underneath the Himalayas at about 2 centimeters a year, and as a result, the Himalayas continue to rise. On the other side of the Himalayas, this collision created the Tibetan Plateau. Year by year, while India moved north, it squeezed Asia upwards. At the same time, some of India also got forced down underneath Asia. Over millions of years, these forces raised the land from sea level to its present height of 15,000 feet. But what does the creation of mountains and plateaus have to do with the Ice Age? The idea that the two might be related came from an unlikely source, the ocean. While leading a scientific expedition at sea, marine geologist Bill Rudiman unexpectedly became interested in Tibet.
For me, it all started with a cruise in the North Atlantic, and we drilled through hundreds of meters of glacial material, and then suddenly you come to a point where there's no more glacial material.
Rudiman was working aboard this ship, drilling long, thin cores of sediment out of the bottom of the ocean. Scientists used these cores to study the Earth's climatic history. Trapped within the cores are the fossilized shells of tiny creatures that lived in the water millions of years ago. These creatures used the elements in the ocean to build their shells. The makeup of the water changes with variations in climate, so the composition of their shells reflects the temperature of the time in which they lived. By comparing the shells from different layers in the ocean floor, scientists can tell when it was warmer and when it was colder, building a record of temperature. Rudiman had drilled down to the time before ice sheets crept onto North America. Now he found himself wondering why it had become so cold that these ice sheets could form.
Comes a time about a year later when you have to, if you're co-chief, you have to write up a synthesis of your results. You list what you found, and then you take a stab at what's going on to explain it.
To do that, Rudiman began looking for other changes in the Earth that might have caused the climate to cool down.
Coming into the literature at that point was evidence for uplift of Tibet. That's a big change because Tibet is a huge feature. So creating that over the last 40 million years, but creating a lot of it in the last 10 million years is a big change.
But did the creation of the Himalayas and the Tibetan Plateau actually cause the Ice Age, or was it just an unrelated coincidence? Rudiman decided to investigate.
I was thinking that we might make a major contribution to solving the problem at the beginning of glaciation, partly because uplifted terrain gets cooler and partly because it turns the winds in such a way that, for instance, there's a more northerly flow into North America, into the area where the glaciers grew. So it was a reasonable assumption that it might help promote glaciation.
Rudiman began by looking at the way wind blows across the region. The mountains and plateau interrupt its smooth flow, forcing it to the north. Over the rest of the northern hemisphere, this increases wiggles or meanders in the jet stream, the higher level winds that blow west to east across the globe. In North America, this brings cooler air from the Arctic further south. Rudiman wondered if this influx of cold air caused the ice sheets to grow.
When Bill came along with the idea that perhaps mountain uplift was changing the wind patterns in the planet in a way that would promote glaciation in high latitudes, bring cold Arctic air further south, this was an exciting idea to me.
To help him figure this out, Rudiman turned to climatologist John Kutzbach.
What I want you to think about is this is a continent, and this is the Indian Ocean. And if we had a low-lying continent of this form, you might get a very weak convection cell with rising air spreading out in the upper atmosphere and then air coming in from the surrounding ocean, perhaps producing a little bit of rain along the edges of the continent. But it just wouldn't be a very exciting circulation because there's nothing on this continent to really focus the heating of the sunlight. If instead we place a high plateau on a continent such as this, all of a sudden the sunlight during the summertime has a real focal point for heating this high plateau. So you have very more active currents of air rising over this plateau, spreading out, sinking, and air literally rushing in towards the continent. In addition to the air coming in towards the continent, the spin of the Earth makes the air more or less spiral in, air coming in off the Indian Ocean, spiraling in over the continent, banging into the Tibetan Plateau, being forced to ascend, producing violent thunderstorms along the face of the plateau. It's easy to understand if you've been in a mountainous climate that mountains affect the airflow and local thunderstorms. But what surprised us was that the effects extended far beyond the Tibetan Plateau itself.
Looking at what might have happened at the time the Himalayas were created, Kutzbach used a computer to simulate weather patterns under 3 different conditions. First, with no elevation in the area. Second, with the Tibetan Plateau at half its present height. and third, with the plateau at today's elevation of more than 15,000 feet.
We've got this box outline where the Himalayan mountains and the Tibetan Plateau are, so you can have that for reference. Then the coloring on here shows the rainfall patterns in the summertime on a world like our present world, but without the Tibetan Plateau. And you see that there's just a little bit of rainfall here in Southeast Asia and over in Africa. Now, if we advance this to our experiment with half mountains, you see that things are beginning to happen. The region of high rainfall has increased over all of Southeast Asia and spreading up onto the Tibetan Plateau. And then if we go to the full mountain simulation, there's even a more dramatic change. Very heavy precipitation on the south and southeast corner of the Tibetan Plateau over southeastern Asia, and a very large dry area extending from the Middle East into the Mediterranean and North Africa.
The computer model was remarkably accurate at predicting the climate patterns in the region today.
It does give you a feeling of power, almost like playing God, to be able to say to the mountains, rise up. And so you crank up the height of the mountain from one experiment to another, and then it's really exciting to sit back and say, oh, what have we done? What do these changes produce?
What these changes produced was a stronger Asian monsoon system, perhaps 10 times stronger than without the mountains. The uplifted land blocks the flow of air from the Indian Ocean, and the moisture in that air falls out as rain over Southeast Asia. The world's heaviest precipitation, as much as 400 inches of rain, falls on the southern slopes of the Himalayas.
I remember still with a sense of delight sitting in my office, and we took the results from the model, and I came to just a very different realization as to how beautifully the uplift of Tibet changes the distribution of moisture, where it's wet, where it's dry, which season it's wet or dry in. And so it actually puts the deserts into the places deserts are, and puts the rainforest in the areas that rainforests are. It doesn't explain everything on the face of the earth, but has a major effect on the patterns of wet and dry climate and vegetation. It's not just on the plateau, but well around the plateau, upstream and downstream.
The computer model showed climate evolving over time as a result of changes in the elevation of the Tibetan Plateau. Now they needed to find hard evidence to prove it. Maureen Ramo, then a graduate student working with Bill Rudiman, helped with this search.
At the same time they were doing the experiments, putting in the half plateau, taking out the plateau completely and seeing what changes in atmospheric circulation there were. At the same time they were doing that, we were doing this vast literature search of how climate had changed in the northern hemisphere over the time interval that the uplift was happening.
Plants are reliable indicators of climate at the time and place they grow, whether it is wet or dry, warm or cold. Scouring the records of previous scientific expeditions, Ramo and her colleagues traced changes in plant life during the millions of years that the Himalayas were forming.
You know, some plant here said this place got drier, and some plant here said that place got colder, and it was just amazing how well all the predictions of the model matched.
But the computer model of the climate of the Tibetan region had one major drawback. It revealed that Tibet's impact on air circulation was just not strong enough to produce the Ice Age.
The results of the model ended up explaining a little bit of almost everything except what we were after. There was really a very small cooling of the Arctic area and the areas where ice sheets must grow.
Just putting the plateau in the models didn't really cause any major global cooling. You couldn't explain why Antarctic ice sheet grew. So it seemed like there still was some other cause for global cooling. This was something I was always thinking about. That was the whole reason I went to graduate school. I wanted to study climate change. And in particular, why the Northern Hemisphere ice ages started.
The main component of climate change is a mechanism called the greenhouse effect. The amount of carbon dioxide in the Earth's atmosphere controls its temperature. Carbon dioxide traps heat from the sun. If the level of carbon dioxide increases, more heat gets trapped and the temperature rises. If carbon dioxide decreases, more heat escapes and the temperature falls. But what controls the level of carbon dioxide in the atmosphere? Most carbon dioxide enters the atmosphere by volcanic activity and seafloor spreading. In the air, carbon dioxide combines with rainwater, making a weak acid that erodes rock. This chemical reaction removes carbon dioxide from the atmosphere. The dissolved carbon then washes into the oceans where organisms use it to make their shells. When they die, they settle to the bottom, forming the ocean floor. As seafloor spreading occurs, sediments on the ocean floor get dragged down and heated, releasing carbon dioxide. Then the process, known as the carbon cycle, starts all over again. One of the first to investigate how the carbon cycle influences global temperature was geochemist Robert Berner.
I've been working on the whole problem of carbon in sediments for a very long time, maybe 30 years. But actually doing modeling of the carbon cycle, we started thinking about the problem around 1980.
It was just an amazing model. I read the paper many, many times. I thought it was just so neat to think about climate this way.
According to this model, climate is largely controlled by how much carbon dioxide enters the atmosphere from seafloor spreading. If seafloor spreading speeds up, the Earth releases more carbon dioxide and the temperature rises. If seafloor spreading slows down, then less carbon dioxide enters the atmosphere and the temperature falls.
The real benefit of studying these models is to evaluate the different processes that affect carbon dioxide, how we circulate carbon from one part of the surface of the Earth to another and to the depths of the Earth. And we can learn more about geological processes by studying the carbon cycle, as well as trying to get at the goal, of course, of trying to get at what controls carbon dioxide over geologic time.
It was a model that explained long-term climate change over the last 100 million years as a function of CO2 in the atmosphere, greenhouse effect hypothesis.
So we think perhaps there's some correlation between our calculations and climate, in the sense that low CO2 could have triggered glaciations by bringing about a reduced greenhouse effect.
But Maureen Ramo thought she saw inconsistencies in the model.
One of the things about the model that didn't jive was that there seemed to be this mismatch between what the model predicted and what really happened in geologic history.
The model did not accurately predict the cooling of the last 20 million years. Perhaps another factor was helping to control the level of carbon dioxide in the atmosphere. Ramo thought the Himalayas might provide a clue.
These mountains are just falling apart.
The rocks that make up the Himalayas are constantly being eroded, both by geological forces and by chemical erosion. This occurs when carbon dioxide dissolved in rainwater makes an acid and reacts with rock.
You can do two things to a rock. You can break it up and you can dissolve it. When you start dissolving it, what you're doing is taking CO2 out of the atmosphere. CO2 in the atmosphere dissolves in rainwater, makes a very dilute acid, and attacks, etches the rock. And when it dissolves, bits the rock, the elements recombine to form new minerals. And in the process, the CO2 that was in the atmosphere ultimately ends up in a carbonate rock. So basically the rivers are the conveyor belt taking the carbon from the land to the ocean where it's effectively removed from the atmosphere.
As the Himalayas grew, huge amounts of rock were exposed to the elements. The heavy monsoon rains combined with carbon dioxide in the air and eroded the rock. Could this process, called chemical weathering, take so much carbon dioxide out of the atmosphere that global temperatures would drop enough to trigger an ice age? Few scientists thought it could.
Generally in the textbooks that I was reading in the early 80s, it was kind of assumed that chemical weathering was a function of rainfall, land area, temperature, these factors. And according to this logic, you might think, you would think that the Amazon rainforest, for instance, would have the most chemical weathering in the world because it had all these factors. But one day I was sitting in a class and one of the professors put up some numbers on the board, and one of them struck me as these were numbers of river discharge of dissolved material, so rock dissolved material. And it was a very high number coming out of Southeast Asia and this area. When I started really digging into a lot of the recent literature, I realized that actually a lot of chemical weathering was going on in mountainous regions.
Ramo wanted to find out exactly how much dissolved rock the rivers higher up in the Himalayas were carrying. Would it be enough to support her idea that these mountains helped bring about the Ice Age? For help in answering this question, Ramo turned to a colleague who specializes in collecting and studying water samples from all over the world.
You have to work in pristine systems, because what you're trying to understand is how the world works as a chemical system. So you have to go to remote areas. Then the problem you get into is, one, just a brute force logistics problem. How do you get there? How do you move around? How do you get out? What do you eat? And the second problem is there's no supporting information. That's to say, there won't be long records of the flow, which you need. There won't be long records of sediment transport, and there very often isn't a supporting information base of geology, vegetation type, and even climate.
Tibet is just such a place. Scientific fieldwork here is still in its infancy. Weeks are spent getting to locations where data can be collected. But such distances seem short when compared to the travels of the nomadic Tibetan herders whose tribes have called the plateau home for centuries. For everyone on the road, meals are a simple affair. Noodles and dried yak meat. Although the plateau is familiar territory to its inhabitants, its vastness is both exciting and frustrating to scientists.
There's huge areas of the plateau we know nothing about. It is ironic that it's playing such an important role in the science in the last few years, and we know so little about it and have so little access to it.
On this expedition, Ramo had the opportunity to collect water samples to learn how much weathering is going on here today.
It'd be very interesting actually to start at the top in Tibet and go right through the Himalayas and see if there's any obvious change in the water chemistry as we go through those formations.
Building a base of information about the region can be slow and tedious. Pinpointing the exact location where data comes from is difficult in uncharted places. But the process has gotten a lot easier in recent years.
You're just taking a river sample, and rather than writing it's, so many kilometers from some town that has a different name on every map, what we're doing is getting a satellite fixed. And this little piece of plastic has an antenna in it. And 20,000 kilometers above us, there's 24 satellites circling the Earth. And this usually can pick up about 5. And what it does is it picks up an incredibly faint signal from those satellites and triangulates an exact position for this spot.
After more than a week on the road, the expedition came to a temporary standstill upon reaching Mount Kailash in western Tibet. Tibetans from all over make pilgrimages to this sacred mountain, which they regard as the center of the cosmos. At least once in their lifetime, they hope to walk around Kailash, an act of devotion that helps accumulate spiritual merit. The team paused for its Tibetan members to make this journey, a hike of about 18 hours straight. Afterwards, the expedition could begin again. For Rameau's explanation of the Ice Age to be taken seriously, it would have to be backed up with hard data. What she needed was a way to show that weathering of the Himalayas had consumed so much carbon dioxide that global temperatures dropped. By accident, she stumbled on a piece of compelling evidence. It comes from a laboratory where scientists analyze seafloor sediment from the last 80 million years. One element they search for is strontium.
Once we get our hands on the samples, we need really only take that material and drop it in some acid to dissolve it. And then we can take the dissolved sample, which, because it's calcium carbonate, really only has 2 major elements in it. It has calcium and strontium. And we take the dissolved liquid, pass it through an ion exchange column, which separates the calcium from the strontium, and we end up with a little white spot in the bottom of a Teflon beaker, which is pure strontium.
There are several types or isotopes of strontium, each with a different atomic mass. They can be separated in the lab, and the concentrations of the different isotopes in each layer of the seafloor can be measured. A heavier variety called strontium-87 comes from the land and is washed into the sea by chemical weathering of rock. The lighter variety, strontium-86, comes from deep inside the earth and is released by seafloor spreading. Maureen Rameau reasoned that by comparing the amounts of the isotopes in the layers, she would learn which process was more active at any point in time, seafloor spreading or chemical weathering. This curve graphs the ratio of the 2 isotopes, strontium-87 to strontium-86, over the last 80 million years. Here was a measure of which mechanism was more powerful in controlling levels of carbon dioxide in the atmosphere.
What we found as we got further into the strontium work was that the curve got more and more interesting. The problem was we weren't exactly sure what it meant. Now, it also turns out that at about the same time, Maureen Rameau and Ruderman had come out with their ideas about how the Himalaya and the erosion of the Himalaya were affecting the Earth's climate, and they in fact used the strontium data as evidence that erosion and weathering rates were changing, and this was support for their ideas. From about 80 million years ago to 35 million years ago, almost nothing happened. And then at 35 million years ago, wham, the strontium curve starts to go up like a rocket in comparison. So if one was going to make a dividing line and say, when was it the way it used to be and when did it start becoming like it is now? In other words, when was the Earth warm and when did it start to get cold? It would have been 35 million years ago. The strontium record was shouting that. If you stretch it a little bit, it's close to the time that India and Asia start to collide and one starts to build the Himalaya.
But is the sudden increase in strontium-87 washing into the ocean at the same time the Himalayas were forming more than coincidence? Maureen Ramo sees it as an important piece of evidence supporting her ideas.
The strontium record was kind of the third piece of the puzzle, I guess, that fell into place, that kind of made it all click. One was, I knew the history of the uplift of the Himalayas. I knew there was a lot of chemical weathering going on here today, but I didn't really have I didn't really have a really good geologic record of how chemical weathering had changed through time. And when I saw a strontium isotope curve for the first time, I saw it at a meeting, and I realized that this was kind of, the smoking gun, so to speak.
The strontium curve is controversial, though. Not everyone agrees on what it actually means. Critics point out that the rising amount of strontium-87 may not be due to an increase in chemical weathering. It could be rising simply because more rocks rich in strontium-87 happen to become exposed on the surface of the Himalayas.
Used for geochemical analysis to see if it's similar geochemistry.
In fact, such rocks are plentiful in the region.
You want an American to whack it off?
No, we're getting there. The granites formed in the Himalayas are exceptionally high in 87 strontium. So what we've got here is a ready source available at the surface to provide the increase in 87 strontium seen in the oceans.
The strontium evidence remains open to interpretation. But another clue to solving the mystery of Tibet's role in the Ice Age may lie just a few days' drive away. In a small town on the Tibetan plateau, the team met up with some local geologists and fossil hunters who had found a rock that they thought might be helpful.
Where'd you get this, Lao Pang? Where did you get this?
潘姐，你在哪里找到的这个？这个门市的。门市啊？不是门市，就是我们这是冈地斯。呀。那个塔庆的北边那条坡面。啊。属于这个第三级盆地里头的。He say he find it in the Tertiary Basin, north of Dachin, in the Kailash.
In the Kailash area.
On Kailash area. He say originally he thought it might be a stem of a plant, but now he compared that with the fossils which has been collected, and this one has been identified as a reed growing on the side of a riverbank here.
A fossil plant, such as a reed that grew by the side of a riverbank, reveals what the climate was like when the plant was alive. A comparison to the same area today reveals how conditions have changed. With enough plant fossils, scientists can build a record of these changes over time. This could help settle another mystery. Exactly when did the uplift of the region occur, and how quickly? The answers to these questions are vital to linking the Himalayas to the Ice Age.
What we really want to know is what the elevation history of the Tibetan Plateau is, and one of the ways that we think we may be able to get at this is using paleobotany. The idea behind this idea is when you climb up a mountain, you go through progressively different vegetation bands. Obviously, it's a lot colder at the top of the mountain. The vegetation is very different. And so, possibly what we can do is look at fossils of past plants that are very high up on the plateau and try to infer what the elevation of those plants were at the time that those plants grew. So, for instance, in extreme case, you'd find a palm tree at 5 kilometers. and that palm tree is Miocene 15 million years ago, does that mean that 15 million years ago the plateau is, much lower at sea level where palm trees grow?
But can you really distinguish warm weather plants from cold weather plants in the fossil record?
If you look at tropical plants, the leaves are generally thick, they're often large, their margins are very smooth. These are called entire margins. Whereas if you look at temperate plants, often the leaves are thin, which is difficult to record in the fossil record, but their margins are often irregular, not all of them, but often irregular. They have teeth on the margins that go around, teeth around the edge. You think of a maple leaf or an oak leaf, you have teeth around the edges. Those are parameters that we can measure.
Will you ever be able to find enough fossils and date them well enough?
No, that's another question.
That's the critical question.
But just a minute, we're in the middle of Tibet now. Is this going to work for us? Is it going to establish at what time the altitude of Tibet was at what level?
Altitude is one problem. Temperature is another. Both are essential to understanding whether the uplift of the Tibetan plateau caused the Ice Age.
I see no reason why we shouldn't be able to trace back in Tibet over the last 20 million years or whatever the variations in temperature. How we translate that into variations in altitude, that's a matter for debate. But as a method for predicting variations in temperature, it seems very powerful indeed.
Well, I personally think it's the only way. And it won't work, indeed, if there are too few species represented. 6 is not enough. We need 20. 20 is a rough minimum. Whether there are enough fossil localities, that's a good question.
To develop a reliable record of the history of the region's elevation by this method would require a wide range of plant fossils. Because this area is so inaccessible, many years and many more expeditions would be required. Field work in these conditions is never easy. The roads are notorious for contributing to the slow pace of science. And it is not just the views that leave visitors short of breath. Working at 15,000 feet is debilitating. Despite how much basic information has yet to be discovered about this region, Maureen Ramo remains steadfast in her opinion that the Himalayas caused the Ice Age.
The Himalayas are unique because they're so huge, they're so high, so much crust has been thrust up into the atmosphere, so much of it has been eroded, that an enormous amount of mechanical and chemical weathering has gone on in this mountain range. It's like a huge sponge pulling CO2 out of the atmosphere. I think these mountains are in large part responsible for all the global cooling in the last 40 million years.
With the addition of the strontium evidence, Maureen Ramo thought she had solved the Ice Age mystery. First, the uplift of the Tibetan region intensified the Indian monsoon. Then the monsoon rains eroded the mountains, stripping carbon dioxide from the air. Finally, with less carbon dioxide, the atmosphere got colder and colder. The only thing left to do was publish the idea.
I went back home and wrote a paper. The paper was an agonizing ordeal, but I went back home and just started writing it. It was short, to the point.
Some scientists loved it. Others were less enthusiastic.
The original paper by Ramo and co-workers in 1988 specified that if we had uplift of Himalayas, the carbon dioxide we consumed by weathering and CO2 would go down. Well, you can't just do this simply because you have to watch out. You run out of CO2 very quickly.
The geochemists are an unruly bunch. They have sharp knives, and if you're wrong, it can be a very public matter.
There was a lot of things in that paper that were very controversial.
I think there's good reasons for why the reaction is mixed. I mean, on one hand, I think some people think, well, gee, could it really be that simple and I missed it? Or the other thing is, well, she can't know enough about this to really get it right. So we are justified in not paying attention to it. But the fact is that it tweaks everybody.
I mean, one of the people that was on my thesis committee just basically said the paper was unpublishable crap. So I mean, I got a lot of conflicting advice on that paper. Some people said, oh, this is great. Other people said, this is crock.
Scientists are men, unfortunately, usually men in white coats seeking after truth about 1% of the time. The rest of the time, they're like everybody else. And so if you've spent the last 10 years making more and more elaborate models or experiments, whatever, it's not just modelers, and somebody comes along and says, that's all by the way, because you're not addressing this, and this is what's really the big problem, then the response isn't open-handed enthusiasm.
There's something about it that's undeniable, and that is that if you erode continental rocks, you should take away CO2 from the system. And if you look at the geologic record, there's been a lot of erosion in the Himalaya. And I don't think erosion was there before the Himalaya formed. So there's been some change since they came up. But if you look at the other models for how the climate system works, they're almost completely at odds with this idea. And there's a real scientific problem. So on the one side, if you listen to Maureen, she will tell you a story that you have a hard time arguing with. And if you go to another person, for example, Bob Berner, he will tell you a story that's almost completely at odds with what Maureen will tell you and give you good reasons why that has to be the case. And so we have a problem.
Things are definitely not perfect with my theory. There's major areas where I don't have an answer. But I think that, that I'm going in the right direction. And I think I know what the problems are and how to go about trying to solve them. She says, hopefully.
Ramo and her colleagues have added to the possible explanations of the Ice Age, but the mystery is far from solved.
If you put up a theory with no fact, it's probably doesn't affect anybody. It just gets ignored. And she, of course, has not done that. She's got a lot of facts to back it up, but we still have a ways to go. Science, the forefront of science is a very fuzzy area, and one needs a balance of all kinds of approaches. There have to be ideas drifting around. They have to be formulated and worked up well, and usually when they are, there still aren't enough facts.
So while scientists continue to accumulate facts that tell us about our climate's history, some cannot resist speculating about its future.
If I was asked about what the climate was likely to do in the future, I would probably focus on the last 2 million years of the strontium curve, during which time the strontium ratio has gone up at a rate that's as close to as fast as it's ever gone up. And in the past, when that's happened, it's meant that the climate is going to get colder in a couple of million years. So my prediction would be that we haven't seen the most intense ice ages yet.
It would be a heck of a story if it turned out to be true.
The highest plateau, the deepest canyon. Take on Tibet's extremes of land and weather at NOVA's website. Log on to pbs.org. Educators can order this show for $19.95 plus shipping and handling by calling 1-800-255-9424. And to learn more about how science can solve the mysteries of our world, ask about our many other NOVA videos. Nova is a production of WGBH Boston. Nova is funded by Merck.
Merck, pharmaceutical research. Dedicated to preventing disease. Merck, committed to bringing out the best in medicine.
And by Prudential.
Living well isn't about being rich. It's about freedom and independence and taking control of your future. So make a plan. Be your own rock.
The Corporation for Public Broadcasting and viewers like you.
This is PBS.
Next time on Nova. On patrol in the Persian Gulf, tensions remain high. Top Gun pilots are at the ready, catapulting into the air at 150 miles an hour, then landing caught only by a hook. 5,000 men keep 80 planes constantly in the air, alert and ready to carry out any mission assigned to the aircraft carrier. Next time on Nova.